I want to welcome everyone to Teledyne DALSA's webinar on selecting the right camera for vision applications. I'm Maureen Clancy, Marketing Project Manager for Teledyne DALSA Industrial Products. Today's webinar will be presented by Fernando Serra, who is a machine vision specialist for Teledyne DALSA Industrial Products. So Fernando, I'll now turn it over to you.
Thank you, Maureen, and welcome to this seminar. We're going to cover a couple of things. This is more than just picking up the right camera for your application. We're going to look at selecting the correct resolution, what's the best optics and camera combination to meet the application requirement, and what kind of lighting do we do to accentuate the features or bring out the features that we're really trying to inspect with good reliability. Image quality is really key in machine vision. You have to always try to get the best image quality you can to get a really robust vision system. Sometimes it's possible, sometimes it's a little more difficult. So, in that in mind, you got resolution, the number of pixels, and whether you have a CMOS or CCD sensor. And I'm not going to go too much into detail because there's other presentations that cover the difference between CMOS and CCD. Optics, the lensing, working distances, and focusing and depth of field, lighting. Again, as I mentioned before, strive to consistent lighting, that things that amplify the objects that you want to inspect for and attenuate anything that's in the background that you don't care for. So you got that reliability on the vision application. There's a wide range of applications. For example, if you want to do code reading, 2Ds, lot codes, part measurement, you want to do certain features, measure angles, distances. The defect detection. Again, this is one where a lighting is very, very critical to enhance the kind of defect features that are looking for in the areas that you're looking for. Guidance. If you have a pick and place kind of applications where you want to find XY coordinates of a part as well as rotation. How about color, where you want to identify if you have the right color on the right locations or the right number of parts, the right color. Assembly verification, places where there is in process and you take a picture after a certain amount of processes in your assembly, and then you want to verify that those processes were done correctly and you have all the components the right way and there's no defects on the components. So let's move to sensor selection. We're going to talk about 2D, 1D, color and things like that, when you would need and where is the right choice for the application. So when selecting a camera, it's really application dependent. Are you looking for accuracy measurements? Are you looking for color or monochrome? The speed of the acquisition, the environment that the camera is going to be in, and sometimes whether you can do the application with area scan or line scan. When you look at the applications, okay, what are you looking for? Are you looking for presence of absence? Are you looking to measure a part? Are you doing a pick and place? Is the material web or continuous? Are you reading 2D, 1D code, or you're reading text? If you're doing measurement, the accuracy is best determined by the field of view. So what you want to do is determine an optimal working distance in the field of view. For example, if you're looking for a really high accurate measurement, you got to try to narrow the field of view because, again, the narrower, the smaller the field of view, your accuracy would go higher. Yes, you can do it with the different type of sensors. You've got a standard VGA 640, 480 all the way to 12 megapixels, 33 megapixels, whatever you're looking for. But again, you get realistically, people come to me and say, well, I have a 12-foot field of view and I'm looking, or a 12-foot part, and I'm looking for 3/10 of accuracy, well, that's kind of near impossible unless you have to break it into different cameras and so on. So again, what accuracy are you expecting to achieve, and can it be done with a single camera? Is it even possible? Just like I mentioned, 12-foot part, and then you want to do 3/10. And for better results, always think of 10 times what you're looking for achieve, if possible, to get even better accuracy. Because again, you're going to have some errors, and you want to be better than the numbers that you are expected to come up to. To determine the sensor size for the accuracy, here's a couple examples. If you're just doing flow detection or just counting objects, consider at least to have 3 to 4 pixels for the object. So as an example, let's say we have an field of view of 12 inches, and the minimum object size that you're looking for is 1/4 of an inch. So if you divide the field of view by the defect size times the number of minimal pixels, you'll see that you will need 144 pixels for this. So a 640 camera will be plenty of that. If you're doing a measurement or a pick and place where it's a lot more critical for the accuracy, here's an example. You have a field of view which is 2 inches, and you want an accuracy of 10 thousandths. So for example here, you take the field of view and divide it by the sensor size, and that will give you the inches per pixels. So 2 inches divided by 640 pixels in the sensor gives you 3 thousandths. If you go to a larger camera, you take the 2-inch field of view and you divide it by the 1280, and that will give you 1/1000th of an inch. Again, this is just pixel camera. I have not taken into considerations subpixel accuracy and all that other stuff that, in addition to what you can do with the sensor. How about when you have a large object, like for example this pipette, and you're going to get to an accuracy of tens? Well, there's another technique that you can use where if you use 2 cameras, and between the 2 cameras you have a calibrated object, and you see these plates on the top and on the bottom, or left and right. You see the whole part. You don't care about anything in between the part. You care about the ends, and you want to measure that really accuracy. So if you use 2 lower resolution cameras with a calibration mechanical piece that you know the exact distance, then you capture the top of the pipette, the bottom of the pipette, you measure the offsets from those calibrated pieces, and then you get a really accurate measurement. Again, instead of trying to measure a 3-inch full of vision field of view and then waste a lot of areas. People have done it too with drive shafts, wheel bases where so big, and they really don't care much about any of the metal part, just at the ends how accurate they measure. How about color versus monochrome? Ask yourself, do you really need color? There's a lot of applications that, if you're looking for color presence, for example, the line image on the left, you see that this is a wire or a placement on wires, and you want to make sure that the correct color wire is on the correct order. So this is really a good application example of what you would need a color camera. The images on the right are 2 objects that are different color. One's a blue and one's a green, and there's enough contrast to determine if one's blue, one's green. So you could do it with monochrome. When you have color, it gets a little more complicated as far as the lighting too. Now you have to use white lights. You have to do white balance so the colors are correct. In the monochrome, again, there's also things you can do where you use a green light to enhance reds and so on. Depending on the color of LED lights that you use, it would bring up enhance different colors. So again, not necessarily to have a color camera when a lot of times a monochrome will do the application. So those are questions to ask yourself. How about speed? Well, how fast is your product moving? For example, if we take the camera acquisition and then the processing to do that inspection, it's equal your total time. I should add as well any I/O, but the I/O could be added to the total processing. So if we take the extender 30 frames per second camera, that's just acquisition, it's 1,800 parts per minute. If we take another camera, for example, one of our CMOS cameras that does 297 frames per second, that's 17,820 parts per minute. Again, this is just acquisition. Then what kind of processing are you doing behind that? Is the vision system powerful enough to be able to keep up with this? I'm not sure I've seen anybody processing 17,000 parts per minute, but we're getting there. Electronic shutter. Cameras have electronic shutters now that allow it to freeze motion. So you don't have blur when you have parts that are moving quite a bit, in quite speed. But you need enough light to be able to bring the shutter down. Again, all the shutter does is stops the images from being burned on the energy into the CCD or the CMOS. So the more light you have, the faster that image will burn into the CCD, and then you transfer it. We're talking about shutters of microseconds. Using strobe light, I have my experience. Anything that you run over 300 plus parts per minute, unless you're doing a really bright backlight, you would need strobing. You can strobe the LEDs. One of the nice things about strobing LEDs, and I'm only referring to LEDs in the lighting because it's been probably 5 years since I don't use any other lighting by LEDs. So the new LED technology, you can take this little guy and pump up 4 amps of current, which will make the LED really bright, but for a very short period of time. You can't run 4 amps constantly, or you'll see the LED pop. So again, think of all the combinations and then the speed that you need in addition to that. As an example, when somebody gives me a really, really critical inspection time, from the point that I get a trigger to the point that I'm responding to the computer, I always like to take a scope and measure. So here's an example of a trigger signal to the output, and the customer wanted to be under 200 milliseconds for this processing time, and I ran these tests hundreds of times to make sure that with all the conditions, from trigger to the time that I sent a signal to the PLC was under 200 milliseconds. And it was really constant. If you see the number below, it was around 189 milliseconds. So again, some of the vision software tells you the processing time, the acquisition time, but if you scope from trigger to output, you get the real true time for it. So do tests, especially again, in really, really tight critical applications. Environment. There's a lot of different environments. A lot of the new smart cameras are becoming or are IP67 or IP rated. You got environments like food, dusty and oily environments, high temperature, and vibration. One of the things about IP67 is the rating is not for what they call the food rate as far as cleanness is. You need to be in stainless steel. Reason for that is in any kind of FDA food, if you're in the wet area, they wash all the equipment with a chlorinated mixture of water and other components that's very acid or chemical will eat away aluminum steel. So you would need things like stainless steel and plastic or rubber casings for the wires as well. Example of the picture on the left, dusty environments. One of the things you want to do is you want to protect the camera and the lens from getting a lot of dirt, a lot of splatter, because if your image, again, if your quality starts degrading, then you're not going to have a good, reliable results. Temperature, a lot of places that require high temperature, especially if you're closer to like a press or some kind of a furnace. So try to keep the image cool or the camera cool, with cautious that not to create condensation inside where the camera is, or then you'll start fogging up the lenses for the CCD. Vibration, I usually recommend people to mount the camera on the same kind of mountings where most of the products going to be running, so they're within the same harmonic. Stay away from like big pounding drives. Usually, people mount them. They put a structure right to the concrete, and they mount the camera on top to attach to a conveyor. So take into account all this when you are putting your camera in your factory floor. How about web? If your product is web or it's continuous, do you use a frame camera or do you use a line scan camera? Well, I have a lot of customers that have web material, and they're looking for maybe a rip on the edge or some kind of random defect that happens, a hole, so it's easy to detect. And they use multiple frame cameras across the web. But then on the other side, you have customers that would like to do looking for very small defects, very particular on film, whether you're looking in the micron holes or contaminants. So that's, I believe, a much better area where line scan would do the job. So if you do a line scan, how do you select the line scan camera? Again, if you're doing the flaw objects, you should at least be 3 to 4 pixels for the minimum size of the flaw. So again, if we take the same example as before, we take a 12-inch field of view. The minimum defect size is 5/1000ths of an inch. So if you do the math, you take the field of view 12 divided by 5/1000 times 3 pixels, you get 7,200 pixels. So you could either use an 8K camera or a 4K or two 4K cameras tied together. Line scan cameras are basically triggered by the speed of the object or the motion. So if you want to determine the speed needing, you take the field of view 20 inches per second with an 8K camera. So you do 12 divided by the number of pixels, and you get basically 1,000 of an inch per second. So times 20, so your minimum speed is 13,654 kilohertz. So if you use an 18 kilohertz camera, you would be good, or to, like I said, 4K 18 kilohertz camera. If you're reading 2D, 1D, and OCRs, for 1D, use a field of view that gives you at least 3+ pixels per bar. Again, this is if your code is crispy clean and it's perfectly, this is probably, you can go down to 2 or so. But again, you want to have reliable readings. If you want to do 2D matrix, use an field of view that gives you at least a 4x4 pixel per cell. Again, same applies. If your code is really crispy, like the one we have on the left, then you can go a little less. For OCR, optical character recognition, I would suggest to use a minimum of 20 by 20 pixels per character, especially on those dot matrix printing. If you're printing or your numbers are as good as a laser printer as these numbers on the barcode, then again you could sacrifice a little bit, because you will still be very good on those on nice contrast characters. Picking up the lenses now. Everybody out there has tools. A lot of the lens vendors have customized tools that allows you to give you sensor size, your working distance, or available working distance that you have, field of view, and then they can suggest the best lens for the application. One of the things we need to worry about lensing is, we always recommend megapixel lenses that give you are good for machine vision, because again, if you're trying to do measurement, you want to or you're trying to get the best image, you want to use a very decent lens, not something you pick up in a yard sale. Um, some of the components, again, you've got to worry about lens distortion, especially, again, when you're doing gauging on the machine vision system. So usually, you know, the more parallel, the shorter focal length. You got perspective issues. For example, if your camera cannot be directly on top of the object, you got perspective distortion. So the part would have a depth of field issues. Complicates measurements, complicates the inspections. Yes, you know, there's a lot of calibrations that are available on the vision system that allows you to correct for this. But if it's possible, try to get, you know, as close to making a flat part as to make your programming simple. Machine vision can measure depth as well. We can use triangulation, Moire, interference, etc. It's still difficult, you know, because the resolution is not as good when you use like a structural light to base your triangulation, and near impossible to see through holes. A lot of people want you to stick a camera and say, can you see all the threads inside to see if the threads on this knot or whatever tap hole have any contaminant. It is really difficult. And again, try to make the camera perpendicular to the part as best as you can. Another effect that you have with lensing is vignetting. You know, the iris or the proportional, you get the cosine. So most commercial lenses usually use the center of the lens, so they try to get the most intensity. So you don't have drop off on the outer lenses. So and worse than short focal lens. So because you have the spot correction. When you're doing measurements, stick to telecentric lenses. Again, especially high accuracy. They have low optical distortion and vignetting. Very good for precision measurements. Very little perspective. One of the drawbacks is the field of view is the length of the diameter, because if you can picture what you're trying to do is you're trying to bring that field of view straight up to the lenses instead of trying to bend it to try to fit, you know, a 5-inch field of view into 2/3 of an image. So they still have some depth of field limits, and one of the things that is not so great is that they are expensive, sometimes 4 to 15 times more expensive regular machine lenses. But again, if you're trying to design a vision system to do measurement, you don't want to compromise and not get the correct measurements because you're trying to be trying to lower the cost. Last thing we talk about is the lighting. You know, again, image quality is the key. There's a lot of different lighting techniques. Your backlight, your rim lights, your dark field. Here's a part, and it's illuminated with different types of lighting. Considerations, again, try to maintain constant light, consistent over time. If your light starts degrading, then you're going to start having problems. Even illumination, again, if your illumination is nice and flat, then you're not going to have bright spots or shadows, and again, your results will be in a really good, robust vision system. Try to block the environment light changes as much as you can, but you know, when you have this consistent light, it does a good job. Optimize contrast, again, as we mentioned in the beginning, trying to enhance the features that you're looking for to inspect, and then, you know, attenuate anything that you do not want to be part of the inspection. So again, choose the right light source to perform the best thing. So as far as illumination techniques, you got backlighting. Again, light transmits, except opposite to a camera, whatever blocks it. Incident lighting, you got, you know, ring lights, diffuse on-axis lights, domes, which is diffuse uniform lights, and you got dark field, low-angle illumination, and then you got color lights as well as infrared lights. Again, here's that silicon rubber piece with a camera. What they're looking for is the number of holes, and where they are, and Backlight does a good job right on the conveyor. So again, light goes through the holes, does a good job, passes the light. It's good for locating, good measurements, and then that's probably the best lighting you get for, again, for doing accuracy in the measurement. Just kind of like a shadow graph. So if you have a transparent light and you want to measure if you see the filament on this light bulb with a backlight, basically that would absorb block the light, and the rest of the bulb would do the same thing as the connector if you want to count the pins. Ring lights. Ring lights, basically they point straight down from the camera, center of the image, the light reflects back, and based on the reflection emphasizes surface, and low angles especially would do that. It's good for illuminating flat surfaces. So here's a good image for a ring light. It's a stent, you're looking for the edges. Array of lights, now that's just a array of LEDs that you can place on the same side of the camera, and depending on the angle, how much light will reflect back to the camera. It's pretty economical. It's used for a lot of configuration. If you're doing things like, for example, labels, you get a nice flat label and the light's not straight on, so you're not going to have that saturation. You have pins again. You have the light on a bit of an angle, so some light does reflect back to the camera. Diffuse on axis. This is a nice, even, flat for especially reflective objects. So again, very uniform light. So in this case, you have a part where you want to look at that 2D code or that OCR. You can still see some of the machine marks there, but it does a nice job attenuating any shiny part on the part, giving you the code really to stand out. Again, on the missing connectors, that's a nice job flattening up the plastic and enhancing the pins. The dome, this is probably the most uniform light available, and it's really good for parts that are very shiny or has a lot of surface and bumps. So here, for example, here's a metal piece that has a lot of the machine toolings and some edge damaging, but with a dome you can get a nice inverse silhouette, which everything's bright, and you get a nice ring right around it so that you can get good edges. Dark field illumination, it's a low angle ring light, and what it is it allows us to emphasize and raises the features. For example, if you look at these images, this is an Allen wrench with a bright field, just a ring light. But when you use a dark field, you can see the characters and the type, and the holes come out really enhanced. On the right side, you have a piece of aluminum that has a laser etch 2D. And look what happens where the 2D really gets brought up. It looks really, really nice. So very nice image of a 2D. Color and infrared lighting. Again, we talked about in the color versus monochrome. Using combinations of colors, you can enhance things that are picked up in the inspection. Green would enhance red and so on, and then it allows you to have a lot more play. Cameras are very sensitive to red, and that's red LEDs are the less expensive one. But there's a lot of combinations. A lot of times you have cameras facing each other, and you have lighting. You can use a blue light and a red light, and then filter that from the camera, so they can still fire the lights at each other, but the camera filters out, or the filter on the lens filters out the lights, so it's independent. They don't get washed down. Infrared lighting is also good because it flattens out all the colors into just gray, and black does absorb infrared. So coming to the end, again, the machine vision is very key to improving product quality, but again, you want to make sure that you take into consideration your factory environment. Pick up your task that you want to do well-defined and machine vision to perform, and then spend time selecting the right combination of camera, resolution, lens, and lighting. Again, good image is key. Understand the performance criteria and the limits of the technology that you pick, because if you try to go beyond the capabilities, you will fail. And pick a solution that will satisfy the current and long terms. Always think ahead what's coming up on the pipe that will help you grow with this vision system.
Thank you, Fernando, and I want to thank everyone for joining us.